How you doing? I'm Mr. Rose, and today we're going to start talking about electric potential and electric potential energy. To start, however, I wanted to discuss a question that keeps coming up. Why does excess charge, that key excess, why does excess charge only reside on the surface of a conductor? Now, obviously, you're noticing that I'm not in this video. It's just the voiceover. I'm interested to see how this goes, so please feel free to give me some feedback. So let's start out this question by, again, examining this reoccurring question. Why does excess charge exist only on the surface of a conductor? Well, to do that, I'm going to state something that should be fairly obvious, right? I'm going to state that excess charge, we're going to make a statement. Excess charge is always free to move if and only if there is an electric field. Meaning, if the electric field is zero, charge is no longer moving. There's nothing that's going to cause that charge to move, right? So, if my electric field is 0, newtons per coulomb, charge doesn't move. Excess charge won't move, all right? This is kind of our basis of electrostatics. So if we have a charged object, right, there's some object that exists, and in the problem, or for whatever reason we're talking about, there is a charge density around this object, we're stating that an electric charge exists around that object. So the charge that moved, right, that's causing this charge had to settle somewhere, right? Charge is going to settle. Well, we know charge is going to settle with charges furthest apart. Again, every time I'm speaking about charges here, I just spelled the part wrong. Every time we're talking about charges here, I'm talking about excess charge. And we know that the charges are going to settle, or they're going to migrate to the lowest possible energy state, right? So as these charges settle, they would have migrated to the lowest possible energy state. All right, so how are we going to connect all of this? Well, let's take the opposite. Let's say if there was an electric field, right? If electric field did not equal 0 in the center, I shouldn't say center, I should just say inside. Inside my charged conductor, I would have, that would yield moving charge. And what would that mean? That would mean the surface of my conductor would be continually changing charge. That would mean my object is gaining a net charge. Because I'd have some charge flow, right? I would have charge flowing because of my electric field, which means I have to understand, since that's not happening, that there is no net electric field inside my conductor. Well, if there's no net electric field inside my conductor, here I drew a surface already, and inside, I'm not sure if you can read that, I dotted this as a Gaussian surface. So I'm enclosing some part of my object. And my Gauss's law states that the surface integral of E dot dA is equal to Q enclosed over epsilon 0. Right? Well, I know when I take the antiderivative V dot dA, I'm going to have the A, but this is some arbitrary object. I don't even know what that area is. However, I don't care about it. I don't need to know that because I know by definition just that if there's an electric field inside, I'm going to have moving charge, which means there is no electric field. If E is 0, I'd have the surface integral of 0 dot dA equals Q enclosed over epsilon 0. Well, epsilon 0 is a constant. My dA has to be an area, which means Q enclosed must be 0 coulombs. So this is a simple explanation on why the surface charge on a conductor has to be 0. So we're going to continue now by talking about electric potential. Again, I've jotted some notes down. What we know so far, really, physics is kind of the story of everyday life, right? We've talked about underlying concepts. We've talked about Newton's laws. We've talked about forces due to gravity. We've discovered that forces can be conservative and non-conservative. We've discovered conservative forces lead to work, energy, and energy conservation, right? And that essentially is all of mechanics. We can even talk about planetary motion in terms of energy, energy conservation, momentum, and momentum conservation. Well, then we're jumping to electricity and magnetism. We're going to follow those same processes, kind of. First thing we started talking about, field theory. Well, we had gravitational field theory. Now we have electric field theory, right? And we paralleled that to our gravitational field theory. Then we started to use Gauss's law, and we started talking about Gauss's law in terms of electric fields, electric forces, and how that affects charge. New to the story now, we're going to start talking about electric potential. Now I'm starting with this statement here, right? Electric potential, people often confuse with just the word potential. Now, potential is usually referred to as electric potential energy. Now, here's my statement. Electric potential and electric potential energy are very different. And just like we've done in the past, we're going to start to parallel some of our mechanics, right? So let's start by talking about potential energy, right? We know by definition that a change in gravitational potential energy happens if and only if I take an object and I move it to between 2 points, and I relate that by doing some negative work into that, that negative work, and some negative work has to be done by a force. What does all of that mean, right? This should be kind of straightforward. I take some box, I'm going to label this spot B, I'm going to label this at spot A, I'm going to label some height H, and what I want to know is, well, what's going on if I say I drop my box from point A to point B? What exactly is going to happen? Well, obviously we know that the force of gravity is going to do all of the work to get my box A moving from A to B, which means I can define a potential energy or a change in potential energy, right? I can state right off the bat that my potential energy, all with respect to the Earth, my potential energy final minus my potential energy initial, right? Well, wait, that would be my initial, that would be final because gravity is doing all this work on my box, is equal to a change in potential energy. Now, my statement was my change in potential energy has to be negative work. Well, where's that negative work coming from? My statement is I know I've got some mg, and it happened because I'm at some height h above the ground. So one more time, by definition, the change in gravitational potential energy of an object between 2 points is related to the negative work that's done by some force. And again, all I need to do in this case is drop this box because this box exists in, obviously, my gravitational field. So continue, it's a little bit cut off. You know, I took from our last page, my change in potential energy is my change in delta U, which I skipped by mistake, negative work, which is negative mgh. So really, again, we know our work definition. This is essentially, we can say that work is my force times my change in any distance where x is representing, it could be my change in height, horizontal, it doesn't matter, x is arbitrary, And we can see from our potential energy equation that this is my force, h is my height, and again, we're losing potential energy. And why are we losing potential energy? We're losing potential energy, put that in quotes, losing potential energy because we're gaining, put that in quotes too, we're gaining kinetic energy. And that's happened because as my box falls, it is going to accelerate and get faster and faster and faster. So we're going to make a parallel comparison here. Parallel, no pun intended. Here I've already drawn out a parallel plate capacitor. We don't really know what that is. Really just two parallel plates. And inside that parallel plate, I'm going to put a test charge, Q, which we know is positive. So first thing I'm going to do is I'm going to draw an electric field. I know my electric field is going from the positive to the negative, and I'm assuming it is a uniform electric field. So I'm ignoring any fringe effects, and I'm also assuming that this distance here from the top to the bottom, which, let's see, I can label distance D. And I'm going to label that from point A to point B, very similar to what we did before. So from point A to point B, I'm assuming this distance is much smaller than the distance of my actual parallel plates. So what is going to take place? Well, by definition, work can't change, but now we're talking about electrical work, right? The electrical work, or more correctly, my electric potential energy to move this charge from here to here. It wouldn't take any energy to move my charge horizontal, just like I would not be changing my gravitational potential energy if I moved this box along this side. So I'm going to note that moving horizontally or perpendicular to my field is kind of like free, and it's not free energy, but it doesn't take any energy to move. My energy work, or my change in potential energy, is only going from the top to the bottom. So really, what I'm going to do is I'm going to correctly talk about a change in electric potential energy when a point charge is moved. If a point charge is moved, right now I was going to say at some angle other than perpendicular, but right now I'm just going to say from point A to point B. And you can obviously see that that's going to be parallel with my electric field, and that might be my maximum when we start talking about things. So this is going to be actually negative work done by my electric force to move it. How is this going to be negative work done? So first of all, again, remember, work is a scalar quantity. However, we can use those positive and negatives to define our direction of energy. Well, we know that it's going to be negative work done because as this charge moves down, it's going to be gaining kinetic energy, right? Q is going to move in the direction of my electric field from the positive plate to the negative plate. So my work done is negative because it is gaining kinetic energy. This is very similar to my mass moving in my gravitational field. It's exactly the same exact concept. We're starting with our maximum potential energy in that field, and as it falls down because of the positive charge, it is going to gain some kinetic energy. Therefore, I'm going to make a statement that my maximum potential energy or electric potential energy exists when it is closest to my positive charge. My maximum kinetic energy exists when it's closest to my negative charge. The net change in energy is zero. It's just changing forms of energy. So I'm going to keep this comparison going on. And what I'm going to say is my change in potential energy. Again, I know I'm going from potential to kinetic. I'm transforming energy. My change in potential energy is, in this case, UB minus UA. And we know, again, that's going to be the negative work done. which by definition of work is my negative force times my distance. I have F dot D. And now we're going to start to use some electricity things. Now my force, we know, is my charge times my electric field times D. That guy right there is my electric force. So this, by definition now, I can say my change in potential energy inside that uniform electric field is negative QED. Right? So this seems to be nice and easy, but we've still avoided this electric potential. And the only thing I've said so far is that electric potential is different than electric potential energy. Okay, so now, excuse me, we change things up a little bit. Again, very similar to what we've done with gravitational potential energy. I've got some charged object here, and I brought my test charge some very big distance away. In fact, why don't we just say that right now Q is infinitely far away from my charged plate? Well, I know if Q is infinitely far away, I'm going to set my potential energy there to be 0 joules. And now what happens if I'm going to apply some force? In other words, I'm going to bring Q into this charge. Well, if I'm going to bring Q in, right, if my rod here is positive, that is going to do what? That's going to require work, right? It's going to require work because it requires force. Now I physically need to apply some force on that charge to bring it all the way in. So as my positive test charge does things like comes closer to my charged rod, work is done on positive Q. All right, well, that seems to make sense. Well, if work is done, I'm just going to rearrange my work equation, right? For a second, I'm going to say that my negative change in potential energy divided by that charge is equal to my electric field times my distance. So all I did, I kind of get the old paper, kind of being a little tricky here. I know that the work done, work is my change in potential energy, QED, and I know QE is my force, but I separated that out, and now I'm saying energy per unit charge or work per unit charge is equal to my electric field times whatever distance I need to bring that in. So what is this that we're talking about? What exactly is that? Now, essentially, now we know it's not a force, so I'm putting that in quotes. This is kind of like the force to move any charge in the presence of a field. Again, it's not really the force, but I know if I have a larger electric field, we would need more of a push, which is why I'm calling it kind of essentially a force. If I look at the units, my units are a Newton, how much force, and then, let's see, distances in meters, Newton per cool, right? It's how many newtons I need to push depending on how far and that charge, right? So again, I'm misusing this word force. I don't want you to start thinking that, but I want you to try and think of this analogy because essentially it's going to help us understand what this electric potential is, right? This force, right, this force that I'm calling is not actually a force. Exactly, I just said it. This is defined as my electric potential. Right? And what that means is the amount of work done the amount of work done, or I should say needed, to move a charge from some point in space, from any position, excuse me, we'll say, I don't know, infinity is usually a good place to start, to some point inside that electric field. So my electric potential, by definition, my electric potential, which is given to us by a capital V, is the negative work moving something from infinity all the way, divided by its charge, which essentially is my change in potential energy divided by charge. Now we need to know that electric potential is a scalar quantity, just like potential is a scalar quantity. And we also want to remember that it can be positive or negative due to the work energy theorem, and also due to the field, because here our electric fields are allowed to change. In other words, if this was a negative charge, we would have a different positive or negative value. So the electric field essentially exists, and wherever an electric field exists, it carries with it some electric potential. What exactly does that mean? Again, we're going to parallel this to gravitational potential. So like I said, if there's an electric field, there is electric potential. So again, let's go back to gravitational. I think I just spelled that wrong. Potential. That's embarrassing. Gravitational potential. What is gravitational potential? Like, what does that mean? How does it exist? Well, gravitational potential, there's my Earth, exists at any point above a mass. We're still talking about gravitational potential energy. So gravitational potential exists right there. And gravitational potential energy exists once I put a mass there compared to that of the Earth. Right? In other words, it's the mass in gravitational potential energy that's giving us this gravitational potential energy. Its potential is always there. Well, this is the same thing for electric potential, right? Electric potential energy, U equals Q times V, electric potential, just by rearranging my electric potential equation, where now this is my potential energy. And what are the units here? This is a charge. I just said units. What is going on this side? This is a charge, and that charge is multiplied by electric potential energy per unit charge, right? Electric potential energy, EPE, per unit charge. Now, I know that seems silly, but charge, potential energy is potential energy. So electric potential and electric potential energy are very, very, very related, but they're very much different entities. We can clearly see that electric potential energy is not the same thing as electric potential. So essentially, and I'm going to say this definition slowly, potential energy is a property of a system or a configuration of that system. We often associate potential energy to a single object in space. However, that space is just defined as the potential. If there's a mass, or in our electricity example, a charge that is placed inside of that field, that is where the electric potential or gravitational potential energy comes from. I hope this was informative. I hope this new method is a little bit better, though it's a little bit longer. Please send me your feedback, and you'll hear or see me next time.